In this video, I'm going to talk about the Voronoi diagram, and we're going to also study a project related to this, which is the Torre de Especialidades. I don't know how we can pronounce that, but this is located in Mexico. So I'm going to also explain a little bit about this project, and at the end we will also model something similar to this in Grasshopper. As you can see, we can also produce different results, and we can also change those radius in Grasshopper. So first of all, I'm going to talk about the project and a little bit of the material and why it was made. So first of all, you can see this is the project, and you can see these cells are actually the Voronoi cells, which we can see, but basically they are maybe filleted, which we will also do in Grasshopper. So about the project, you can see that this is the view of the facade, and let's just go forward, and you can see here the details, and the base of the project is to increase the surface area of those modules to also decrease the pollution of the air. So I'm going to explain about that in a moment. So you can see again those Voronoi cells are tessellated together to produce this facade. And again, let's just go further. This is the mold, as you can see, and I'm going to show you in the video how it's made. It's really great to know more about it, and you can see this is one of the modules, and here it goes, and it's really beautiful. So as you can see, again, here are some details about this. You can also look at those images in the website. So let's just go forward. This is the installation. You can see that those sections or modules are installed in the facade here. Let's just go for another picture. Again, you can see this installation thing, and here are some details about the installation, and here we go. This is the finishing inside, the view from the inside of the building, and the view from the outside of the building. So this is basically the project, but let's just go forward and watch this small video. I have just edited this video to pick up the most important parts, so the intro.
This hospital tower also has a very unique feature. It eats smog.
So you can see that these modules eat the smog because of the increased surface area of the modules. So
this facade is coated in a special material, which, when hit by sunlight's UV rays, begins to break down pollutants. Designers say it neutralizes the effects of 1,000 cars every day.
The genesis of the design began some 10,000 kilometers away in Berlin.
About the project, you can also know more about the project here in the website. You can see that the Grasshopper is the engineers of this, and more information about the project team and the product specification, especially about the facade technology, which you can see that it just cost $20 billion of investment to health infrastructure in Mexico.
We were witnessing the rise of smart materials and their applicability in architecture. And what we saw was a city full of built structures that were essentially dormant.
The design is inspired by natural shapes. It's kind of similar in appearance to corals. There's a need in the photocapture.
Okay, the natural shapes, we can talk about this, but this can be based on a design of corals, but these can also be modeled by a Voronoi diagram in Grasshopper, which we will just talk about it later.
Reaction for a maximum surface area, and the natural forms of corals, for example, is very good at doing that.
Using a material called titanium dioxide, they developed a pigment that coats the tiles, or so-called modules.
So you can see that the coat is the thing that absorbs the pollution, and also the increased area of the module.
When pollutants come into contact with the modules, they're turned into compounds like water and carbon dioxide.
As you can see here, this little and simple trick in design will increase the surface area of the surface and will absorb more pollution based on the coating of the module.
Side.
We won't reduce significantly the levels of pollution for the entire city, but we do it significantly for a localized area where very high levels of pollution meet urban populations, so we're directly protecting people.
And this, say the architects, is a model that can be applied to any city around the world.
Okay, so this was the video, and let's just go into the Grasshopper section. And I'm going to make this as easy as possible because we're going to take some steps. You can also watch some video tutorials which is related to the Voronoi diagram and producing Voronoi in Grasshopper up this corner, and know more about it. Okay, so let's just get started and start from scratch. What I want to do is to first go to the mesh section, and as you go to the triangulation, you can see that this is a Voronoi tool. So if we just put this in the Grasshopper, let's just put the bifocals plugin so you can see the names. Okay. First of all, I've explained about this in many tutorials, but for now, what I want to do is to set multiple points here. The most important thing about the Voronoi diagram is that you have to have random points, because if you have regular grids, it's going to end up like a rectangle or hexagons. So what we want to do is to be sure to have random points. So the next thing we have to also give the input is the boundary. So I'm going to draw a rectangle, and it should be a rectangle, as you can see here that this is a rectangular input. So I'm going to go to the params menu and pick up a curve and set this to the rectangle. Okay, and that is because it has to trim the cells, and the reason the cells are produced like this on the Voronoi diagram is that because if we go to the mesh section, and up in here in the triangulation we have this Delaunay mesh. Okay, so if I just put this on the Grasshopper here, basically the Delaunay mesh is the base of the Voronoi. So if we just turn the Voronoi off and connect those points to the points, you can see here, let's just move these points so you can better see the results. Okay, you can see that the Delaunay mesh is simply connecting these points based on a near point to that. So if this point is going to reach out for those points near them, they're going to connect into lines. So it's not going to connect with this point, it's going to connect with the nearest point possible. So this is going to be a Delaunay mesh, and this will make the Voronoi. If I just turn on the Voronoi here, okay, and zoom in, you can see that this is simply perpendicular to the Delaunay mesh here, here, and here. And this is also the center, as you can see, that it's colliding with it. So if we just draw a lines which is perpendicular and also dividing these Delaunay meshes lines into two same sections, as you can see here, we will have lines, they will collide maybe at the center or not. Again, if we just go into another cell, you can also see it here. This one was for this edge, but it just collided with this one and this one. So you can see that the center is shifting out from this triangle. So we don't need to do that, because simply Grasshopper gets those points, calculates the Delaunay, and draws the Voronoi diagram. Another thing you have to know about the Voronoi is that if you give this a radius, you can always change that. You can see that another definition of the Voronoi diagram is the circles that have the same radius, and we are increasing the radius. And you can see that if they collide, they will produce a simple line here, okay? And it's going to be trimmed at the intersection, and then the radius is going to increase until all of those circles collide. So that is why nature produces Voronoi diagrams. In nature, you can see that in the leaf venation pattern, you can see that in the soil when it just dries out, so or the pattern on the body of a giraffe or something like that. So it's going to produce also Voronoi cells, and they're going to increase infinitely. So you can see that if I just delete this, this is going to go and be trimmed with the boundary. So we can always change the boundary to whatever we want, and if we just connect the points to that and move those points, you can see that the Voronoi will just simply update. Okay, the next point we have to do for the a project similar to this, because we can't make this in a small tutorial, but we want to make something similar to that, is to go to the, this is the cells. So if I bake that, you can see that we have those Voronoi cells. Okay, if I go to the curve section and use this one, control polygon, and connect that, it's going to give the points of that polygon to me. And we can go to the spline section and use the NURBS curve and connect this to the vertices. And you can see that it's producing something, but there's a point wrong here. So because it's going to go to the end and have a duplicate point, I'm going to use this call index thing and delete the first point. So let's just use the call index tool, give this to the input, and delete the index 0. So I'm going to give a 0 and say delete the 0. Okay, and now we can say that this is a closed curve, so we just go to the periodic inputs and set this to true. Okay, we can also make this a little bit smaller by using an offset. So let's just offset this curve, and because it's just offsetting outwards, I'm going to go to the distance and set the expression to -x. So it's going to go inwards, and we can always give a number to this to make the offset. Okay, you can always make this a NURBS curve. As you can see here, because of this small edge here, we have something like this. So you can go to the last part, and it's using the rebuild curve, and it's going to rebuild this curve with a degree 3. So you can just give this or just use the default, and I guess that the count 10 is fine. And you can see that this is making those, okay, let's just turn this on, making these sharp edges go to smoother results. So you can make that happen by rebuilding those curves. Okay, just turn everything off, and I'm going to turn the boundary back on, which we have it here, and also turn on the rebuild curve here. So we have the rebuilded curve here now. Okay, to make something similar to this, what I'm going to do is to move this curve up here just a little bit, and then I'm going to use 2 points of the curves, connect them, and move them in the normal direction of this line a little bit back, and connect that to an arc. So maybe it's going to be something like this, and then we can sweep that around. So all of them are going to make something like this, and then we will just build the solid. So let's just do that. I'm going to move this a little bit up in the Z direction, and we can just give this a 5.5 is fine. You can just increase that later, so we can just give this the thickness of the project. And by going to the curve section, we can just pick up the point on curve, and the start of the curve is fine, the start of the moved curve, so we have 2 set of points. Then I'm going to connect that with a line in the curve section, the line with 2 points. It's going to make a line here. Okay, and now we have to again pick up the midpoint of that and move that in the normal direction. So how can we extract the normal direction? It's simple. You can go to the analysis section and use this, okay, perpendicular frame tool. We also have a tutorial about this, so I'm going to put up in the card section. Again, the perpendicular frame is going to go for the base curve. I'm going to use it here, And because the curve has a domain, different domains, we're going to right click and reparameterize to simply make this from, if this is the start of the curve, because this is the start of the curve, it's going to be from 0 to 1. So remember, always reparameterize, we'll just make this from 0 to 1. Let's just go to the curve, reparameterize this and say 0, because we use the start of this. And you can see that this will give you the normal direction. This is the direction we are going to move those points. But basically, if it's the x direction, it's going to be -x. So I'm going to go to the vector section, extract or deconstruct the plane into its origin x, y, z, and use the x direction. So let's just move this point. I'm going to go to the math and use a multiplication, so I can give this maybe a smaller number to bigger number and define this. And as you can see, I can move this. Okay, this is going to go in the x direction. We go to the motion expression and type in -x. That is the solution. And now we have 3 points. Let's just turn everything off. We had these two set of curves, we had these 2 points, and now we have this moved points also, move point here. So I'm going to go to the curve section, the primitive, and let's just zoom in. Here we go. An arc with 3 points is fine. So I'm going to use this arc with 3 points. And what we're going to do is this is the start of the arc. Okay, I think I just did it wrong. This is the start of the arc, this is the end of the arc, so this is going to be point A and point C. And the point B, which is in the on the arc interior, we can give this moved point here. Okay, so now we can simply just produce the surfaces. Go to surface, freeform, and produce a sweep to surface. So this is going to be cool because we are using 2 rails, and the first rail is the bottom curve, the second rail is the moved curve, and the section will be the arc. Okay, and now you can see that we have produced that, and you can simply just make this okay, let's just do this. I'm going to go to the boundary in the surface and make a boundary between this border and the curve at the bottom. So if I use the border here, going to the input, and I'm going to shift at the curve we just rebuilt it at the bottom. Shift this here, and remember you have to flatten those because they are in groups. And if you don't know what flatten or graft is and you want to know more, I'm going to put that in the card section again. So let's just flatten this and we're good to go. Okay, so we have this bottom surface here, we have this inner surface here. We're going to move this bottom surface up exactly the same as this z direction, so it's going to go to the top. And I'm also going to again move this boundary up in the z direction exactly the same as the move of that, because okay, I just didn't connect that. This was the motion, yes, okay. And what I want to do is to also loft these 2 boundaries together. So I'm going to go to loft, and we're going to loft the boundary with a shift key to this moved surface. Okay, we have that. So now we have the moved surface, the loft of this border, this one, the boundary surface, and the sweep ones. And we have to just join them together in the surface section, brep join, and remember again we have to flatten because we want to join all of them together. Shift key, add this up, and we can just bake that brep, and we're good to go. Here we have the results, and now we can simply go to the perspective, right click or any view, and head down and go to this, okay, clipping plane thing. Now I can just put a clipping plane and move this in the Z direction so you can see that it's producing something similar. And then we have to also divide those to produce the modules and so on. So this can help you. Again, if you want, you can just use Control-C, Control-V, and move this another clipping plane at the bottom and rotate this, because this is two of the clipping planes are in one direction, so I'm going to give this a 180 degrees rotation and make this, okay, move this a little bit up, and also clip plane the bottom. So you can see that I can always use a clip plane here for smashing the top and another clip plane to cut off the bottom. So here we go, and you can see that this is producing the results, and we can always do that. We can do this in Grasshopper, but I just want to finish this tutorial because I don't want to make it complicated, and this was just a small tutorial to know more about Voronoi diagrams, to know more about the project, to know how you can make that smooth enough to bake that. And you can always remember that you can change the options in Grasshopper, and that is the reason we just made this. We can increase the multiplication to make this a little bit more arc here. Okay, that's another one. We can also change the offset. Where was it? Okay, we can get lost in this. Okay, I can also increase the offset. And remember, you can't just increase that. Sometimes it's going to give you errors, but for now it's fine. We can also increase the thickness, and this is another results. We can also give new points to this. So let's just go to the top and add new points. I'm going to bring this to a new example and increase those points. And here we go. We have to wait to Grasshopper calculate the surface of this. So let's just wait. Okay, and we just go back and we have this. Okay, let me just give this. You can see that this is changing. Okay, if I just decrease that to maybe 5 or 6, you can see that we have bigger ones, and then you can simply bake this solid. Here we go. That's it. So this was the tutorial of how you can also produce Voronoi diagrams in Grasshopper, just make them a little bit more in 3D, produce those fillet surfaces, and also about the Delaunay mesh, which I explained about that. So you can know that the Voronoi diagram is produced by two ways. One is the Delaunay and another one is with the radius. And thank you for watching. Please like our videos, comment below this video. It will just support our channel, and thank you for watching. Thank you for watching, and subscribe to our channel. And you can also watch something that is related to this video, that corner, and see you next time.